Good morning, everyone. Good morning, everyone. My name is Jim Livesey, and I am the Vice President for Research and Innovation at NUI Galway. This is my first chance to talk to members of the tech community. It feels like coming home. My last gig was back in Dundee, where I was co-director of the AHRC-funded Creative Cluster project in digital and video technology. So this feels very much like the first chance to talk to a community that I hope I'll have a lot to do with in the next few years. The main business of the morning is, of course, to talk to Jim. I just want to take a few minutes to introduce myself. I think we have some wonderful opportunities coming that I think we can share together in the AtlanTec community in the next few years. You'll be aware that the European Union has nominated the digital transition, of course, the theme of AtlanTec this year. The digital transition is one of the core pillars of the European Research Agency and the European Research Area for the next 7 years. And there's going to be a huge effort at collective work in this area. And the opportunities this opens for us commercially, intellectually, scientifically are really enormous. And I just want to send the message out into the community that we are really open for business at NUI Galway for collaborative projects and are looking to build the kinds of platforms that can genuinely take on the big challenges of the digital transition and look to work with this amazing community to bring real social benefit and bring all sorts of other good impacts for the community and for the country in the next couple of years. And speaking of such things and impacts and effects, Jim Duggan has got to be one of the most important people in our university. You'll be aware that Jim, as a member of the Irish Epidemiological Modelling Advisory Group, and his role is to develop and deliver epidemiological models to inform operational policy decision making. And could there have been a more important role over the past year and and a half? He's very involved in Pandem II, and he's going to talk to you this morning about key places, I think, where the kind of work that we do in the university and the kind of work that happens in government and in business will overlap. And we're going to be working in this space so closely together in the next few years. And now, without any further ado, I want to hand over to Jim, and really look forward to an interesting interaction this morning.
Thank you very much, Jim, and it's great to be here today. Hopefully you can see my screen here. So again, it's great to be here at the AtlanTec Festival. Really looking forward to the talk today. Again, my name is Jim Duggan. I work in the School of Computer Science, NUI Galway, and today I'll be talking about infectious disease modelling and a systems dynamics approach. Okay, so I have a couple of things to go through in the presentation. There are 4 sections really, and the first section will be looking at the context of modeling, and in particular, because again this theme is the AI theme as well, I'll be drawing parallels with data science and the modeling approaches that we can use to help plan for pandemics and also respond to pandemics. Following that, I will talk about a very famous model that probably many people are aware of. It's called the SIR model. This dates back to the 1920s, and it is a cornerstone of infectious disease modeling, and it's really worthwhile just going through that and trying to see some insights from the model as well. So we'll be looking at, in many ways, what a small model can give in terms of insight. From there, then we'll scale up to a larger model, and this really is informed by my work, as Jim mentioned, with the IMAG group. The whole idea of scaling up to building larger models, and the whole idea of the modeling process, which is really very similar to the agile process for software development. The steps you go through to build a model, the importance of testing, and how the model can be used. And finally, as Jim mentioned again early on, we have a Pandem II project to start at NUI Galway, looking at pandemic planning, and we have 19 great collaborators across Europe, and I mentioned that project as well. So that's the overall structure of today's talk. The diagrams on the right, these will become evident as we go through the talk itself. So moving on then to so myself, my background. I'm an industrial engineer, my original qualification, so I'm very interested in interdisciplinary work. I lecture in the School of Computer Science in programming and analytics, in particular the R and MATLAB platforms. I also lecture in modeling and simulation, and my research interests are system dynamics and data science, which I'll give you more about today during the presentation, and also an application area which is public health modeling. So I've been working in this area with experts in public health since maybe 2012. I've gained a lot of knowledge in the area, and I apply the models to this very important area. In terms of my experience of project work to date in public health, I've worked on the Pandem project. We're now in phase 2 of the project. Again, I've worked with the IMAG and infectious disease modeling. We're also partners with the World Health Organization Global Alert and Response Network and their Go Data project. We've contributed to that from NUI Galway. And I've also worked on the in the public health area of suicide prevention with the Health Service Executive, the School of Psychology, and the Connecting for Life project for Galway, Mayo, and Roscommon. So again, on the right-hand side, just some publications over the years. And again, thanks to the sponsors of research, which are also listed on the right-hand side. So today, the first thing I'm going to look at really is a broad look at the overall area of analytics. And it's really just to frame the modeling work that I present in terms of an approach to data analytics, which is more model-based than database. So there's a very good paper recently in the Royal Society looking at things called mechanistic models versus machine learning. And really, the work I'm presenting today is really mechanistic models, but they're also very closely related to machine learning as well. So the main difference really is, I guess, with machine learning, you have a large data set and you extract maybe unseen patterns that might exist in the data. And again, these are very important techniques, particularly in healthcare, to use them to achieve good patient outcomes, etc. But the other approach you can use is what we call mechanistic models. For example, system dynamics is a good example of that, where we tend to build what we call causal mechanisms, which really means we just build models based on maybe medical knowledge or people's experience. So it's a slightly different perspective, but in many ways it's a complementary one as well. So in terms of some of the, again, from this paper, there's some nice kind of delineation between the two approaches. With mechanistic models, we look to establish a mechanistic relationships between inputs and outputs, whereas machine learning, broadly, we're looking at statistical relationships and correlations. I won't go into too much detail about the differences, other than to say that they, when you go through the modeling and look at, for example, the way we build the model and look at the SIR model, it's a branch of what we call mechanistic modeling. So system dynamics then is a mechanistic modeling approach. It's also, the term simulation is often used as well, and it can be used to design more effective policies in organizations. And the idea really is that it's a general approach. So we can apply this to, for example, manufacturing, to the environment, to many different problem areas. The point is, when you engage with a problem area, you can see that you can build models of these. So here is a very simple model of this is called limits to growth model. So we can model the population of a city, and we see this in a moment as well. We can put these equations together, and essentially this modeling structure here, which is, we call this a stock and flow model, this generates the behavior over here. So you see a common theme here, that this kind of modeling, you kind of have on the x-axis you have time, so you're looking at things over time. So it could be the growth of a city population, it could be indeed the growth of an infectious disease, but the point is the models that you build generate this information over here. And what we can do is we can link this in with data science as well, because we can calibrate the models to fit the data and basically give people confidence that the model is fit for purpose. So that's the general idea of simulation. So I'm just going to describe two important concepts for systems dynamics modeling. It's quite an intuitive concept, but it's a very important one nonetheless. The first one is the idea of accumulation. So when we build these models, we're interested in accumulations, things that build over time. For example, this is a really nice model from a number of years ago of carbon in the atmosphere. And this really is an example of what we call a stock and flow model. In here, we have the stock that builds over time, but the stock will build through things called inflows coming in this direction and outflows. So we can break any model into, you know, this idea of an accumulation of a stock, and then we can look at things that add to the stock and things that take away from the stock. A very practical example of this would be, for example, your bank balance. So your bank balance would have a balance on maybe the first thing Monday morning. As you add money to it, the balance will rise. As you take money away from it, the balance will fall. But that really is another example of a stock and flow system. So the idea then is that stock and flows are everywhere, and we can build models using stocks and flows. We can also, an additional idea of a stock and flow model is a related notion called feedback. And this essentially is that in some models that we build, there is this thing called feedback where a value might depend, might change over time. And what you have is you've this kind of loop effect here. So words like virtuous cycle and vicious cycle, when those words are mentioned, it tends to mean you feedback in the model. An example of feedback is, a classic example would be compound interest in your bank account. So if you win the lotto, you put the money in your bank account, you leave it there for maybe 10 or 15 years, you never take it out, the money will compound over time, and it will actually then generate what we call exponential growth. So feedback, when you have them in models, they tend to drive exponential growth. So we know from infectious diseases, you know, you've got this classic curve like this where you have exponential growth, and that just tells us there's feedback in the model. So when we bring our models together, these two ideas of accumulation and feedback are very, very important. What we will see in a couple of minutes is how these can apply to the classic SIR model. So we'll be going into a small bit of detail on that before then we go and look at the overall modeling process. So we can sum it all up in terms of the general principle of stock and flow systems, and this is a widely studied concept, and people do experiments in terms of how well people understand these and how they can, as it were, envisage how they work. So we have this simple equation, which again you can relate back to your bank balance. As long as the sum of all inflows exceed the sum of all outflows, the stock will rise. As long as the outflows exceed the sum of all inflows, the stock will fall. And if they're the same, and we'll be exploring this in a moment, the stock stays the same, or what we call it stays in dynamic equilibrium. So basically, these three principles underlying the whole idea of a stock and flow model. And what we can do now is we can look at a model of infectious diseases and see how we can apply these principles to the model. But basically, a very short introduction to modeling, and that is the stock and flow approach. So now we move on to the SIR model. This is again the famous model from the 1920s, but it's a core model that a lot of infectious disease models are built from. Over here we can see it's a stock and flow model. So in many ways, what we do is we divide the population into three important categories. Those who are at risk, who are susceptible. So these are people who haven't yet been vaccinated or got the disease. People who are infectious and spreading the disease, and people who are recovered. So these are the three stocks, and they're linked together as well. And basically, we then have, so this is our stock and flow model. What we then do is we can then add these equations for people getting infected. Now, I won't go into too much detail about these. So the stock and flow models, if you remember from your maths a long time ago, that these are calculus equations that run the model. But basically, it gives us a way to model the spread of a disease. So in this model, births, deaths, and migration are ignored. The population is viewed as homogeneous, which basically means everyone has a chance to mix with everybody else. So you have things like the contact rate in the model, which means the average number of contacts somebody has per day. Things like the infectivity, which means that if an infected person meets a susceptible person, basically what's the chance of the infection spreading? So with this simple model, you can actually generate some interesting dynamics. And then once infected, people recovered after a given time lag. So that's the model. The the engine of the model then is this equation, and it's quite intuitive really, and underlying. So when you see the SIR model, there's this equation basically under the bonnet. This is the engine of the model in terms of generating people who get infected. And if you take the idea that, let's say you have 10 people infected, they each contact 10 other people, then you have 100 potential infectious events during a particular day. Then this is the chance of being a susceptible person, and then this is the probability that an encounter with a susceptible person will lead to an infection. So this formula then is really important, and it's the one that drives the simple SIR model, and versions of this drive also more complicated models. But what's in here though is a couple of interesting things, is that, you know, this here is a stock. So, you know, as people get infected, the number of infected people increase, but also as this increases, the number of infections also increase. So this is called a feedback process. And basically it means that this is why we get exponential growth when a disease starts to spread, because we have, you know, as more people get infected, they infect more people. And this continues on until most of the population gets infected if there are no measures in place. So this is the general equation. So what we're going to do is really just zoom in on the stock in the middle and just do like a simple analysis of the equation, and then we're going to think about this from a public health perspective. So in many ways, we're just going to simply zoom in here and say, well, if this is a stock by itself, you know, it increases, this is the inflow, this is the outflow. And we're going to look at the scenario whereby we can compare the inflow and the outflow and maybe relate this to public health measures that can be carried out. So we're going to look at a thing called an equilibrium condition. It simply means it goes back to rule number 3 from the earlier slide. When the inflow equals the outflow. So for example, if you withdraw €100 per day from your account, but you're also lodging €100 a day, your balance stays the same. So basically this is called the equilibrium condition. So if you put all these formulas together, what we get over here is the following equation, which really says is, so for example, the net flow we're saying is the inflow is CIS over N by I. So C is the number of contacts per day, I is the infectivity, S over N is the proportion, is the susceptible divided by the total population, and I then is the number of infected people. So when we put this into an equation, we get this one over here, which basically says that if these two terms are equal, the system is in equilibrium. So, okay, it's quite a simple equation, but what's useful here is we can actually look at the equilibrium condition, and then we can start to do almost like a thought experiment. Well, from a public health point of view, how can we influence this particular equation? So we're going to call this the battle of the flows. The battle of the flows really is, in many ways, it captures the challenge of public health protection. We want to protect the population, but on the one hand, we have this is going to drive up the number of people who are infectious, and then as they recover, they're going to move out of the stock. And in many ways, it's the battle between these two flows. So you really want to, I guess, minimize this one over here and try to improve the chance of people moving out of here in order to help you battle the disease. So mapping the flow equations onto a simple model of public health policies, what we can then do is we can look at these variables over here. So C is the average contacts, I is what we call the infectivity, S over N then is the number susceptible divided by the total population. 1 over D then is the duration of infection. So if we look at this, then we can relate this to different kinds of policies. So with a new pathogen, you basically there aren't any pharmaceutical interventions unless, for example, it could be influenza where you have antivirals. So therefore, non-pharmaceutical interventions become very important. And if you look at this equation over here, what we can say then is that if we reduce the contacts or reduce the transmission, we will reduce this part of the equation over here. Therefore, we will reduce the number of people who are infectious. So in many ways, by looking at this equation up here, CIS over N equals 1 over D, we can relate parts of this equation then to these kind of interventions. So we've non-pharmaceutical interventions, which could include lockdown, restrictions, distancing, or masks. Another non-pharmaceutical intervention would be test, trace, and isolate. So if we reduce this value over here, we will increase the outflow, and therefore we will then reduce this value here. This basically means that, if we can do test, trace, isolate, and we can, for example, reduce the number of people who are moving rapidly into quarantine, therefore they have a less chance to spread the disease. Other options then are pharmaceutical intervention, which could be antivirals, and then the other one then is pharmaceutical intervention, which is vaccination. And we're seeing this at the moment. The key idea behind vaccination is that we're reducing the value of S. And this is a really important thing, because as we reduce the value of S, this value gets weaker because there are less people at risk, and therefore we can then move towards a more normal state where basically we don't have the pandemic running through society. So vaccination then plays a key part in the equation. You can do some simulation analysis of this. So this is a very simple model, but here we can see infectivity is maybe going from 0.5 to 0.10. This is your quarantine fraction. And you see the more, like if you can reduce the infectivity and also get more people into quarantine through test, trace, and isolate, you get lower outbreaks up here. So the point then is that I think really just to close out on the SIR model itself, the idea behind it really is it's a fundamental model in epidemiological, in infectious disease modeling, but also it gives you some insight into what you can do to basically go back to the battle of the flows, where you want to, these two here, I guess, are battling against this one over here. And basically, you don't want this one to win, because if this gets higher, the number of infections rise and you get exponential increase. So hopefully that made sense in terms of the usefulness of the SIR model. What I'm going to do now is, so the SIR model is a very important model, but also you then want to move this into practice and to make it useful in terms of policy and policy support. So in order to do that, you do need a modeling process. So here, I'm just going to go through the modeling process. It's really a 5-stage process. And as I mentioned earlier on, it's very, very similar to the agile development process. So over here, I mean, this diagram shows you the goal really of health protection. So we start off with people at risk, and then at the end, we want people at low risk. So we want to get from there to there. So that's an important journey along the way. And the modeling then is we have these 5 different stages. So modeling is a feedback process. It's not a linear sequence of steps. Modeling involves model builders and also experts in terms of epidemiologists. So this is the process that we can go through in order to build models. So just an idea that the first step of model building is what we call problem articulation. So what is the problem? Why is it a problem? What are the key variables and concepts? So what's the time horizon, past, present, and future? Because again, going back to the idea behind stock and flow modeling is that, we're looking at things over time, how they behave over time. And basically, we want to get an idea of, how is this behavior generated? So here is some output from the Johns Hopkins University dashboard. It shows the Irish, for example, incidence rate for COVID-19. But basically, that would be your starting point for a problem. So what is the behavior over time? The behavior is problematic because obviously exponential growth leads to huge pressure on the health system, and also leads to very, very, very undesirable health outcomes. Okay, so that's problem articulation. The next then we put together, okay, we call this dynamic hypothesis. It simply means that, what are the current theories of the problematic behavior? So as we look at the behavior over time, so it's kind of going like this and then up again like this. As we look at that behavior, can we actually have a theory for what's driving this behavior? And at a simple level, the SIR model, which you just summarized, that essentially is an example of a theory for this behavior. So what we do is we start to build models, and the model then gives us a theory that allows us to replicate the behavior. And essentially, this then becomes what we call our dynamic hypothesis. So it's like our theory of, why is the disease spreading? And again, I think it's important to recognize that a lot of these models are very much informed by medical knowledge. So if you go through the life cycle of infection, you've got different stages. And what you find is when these models are built, they really capture the medical facts underlying the disease. So people are susceptible, people then get infectious, and people then get recovered. These models are really driven by knowledge of the underlying medical dynamics, really, and they come to the fore during the model building process. Okay, then we go and formulate the model. So this is an example of an SIR model that's called an age cohort model. So this is some of the work that we did over the past year. So it just basically means we can break the model down into different age cohorts. But as part of this process, we will actually specify the stock and flow structure, and ultimately we and also the decision rules. We estimate things called parameters. So the parameter could be, for example, how long is somebody infectious? So for example, and also how many contacts somebody might have per day. We look at things like the initial conditions. We also do lots of testing, and this is part again of the model building process. From then on, we go and test the model. So model testing then involves a very rigorous examination of the data, and basically here's some examples of things like fitting of the model. So basically the model is the blue line, the data then are the gray dots, and part of the process then is we want to essentially go through the model and test the model and also calibrate the model as well. So again, this is part of the process, and again, just as we would use the agile process for software development, where we have testing as an important part of it, we do a similar thing with the putting models together for infectious disease. We can then use the models then to formulate policy and evaluate policy questions. So these are things like, for example, what if analysis. So, for example, if we increase the mobility in the population, what's the likely impact on the number of infections? We can do things like sensitivity analysis. So, essentially, at this part of modeling, so if you think of something behaving over time, so basically it could be like this. Maybe you're at this point in time, you've calibrated the model, and then from here you might say, well, there are different scenarios. So maybe it might go one direction, maybe it might go this direction. So these are different scenarios, and these scenarios you can use the model to generate these scenarios, and these scenarios then become part of the policy design process. So basically, they give you a sense of what might happen if we, for example, do X, Y, or Z. We can also do sensitivity analysis. What are the likely impacts of uncertainties? And this again is part of the model building process. So again, this model building process is a key part of it is interaction with the domain experts. So it's very interdisciplinary. We have modelers and also epidemiologists, and this part of the testing and the formulation and this whole process, it relies really on a very good interaction between model builders and also on the domain experts who are the public health experts. So that's really, and this is some of the idea of the toolkits that we use. Again, this is part of the AI big data stream of AtlanTec. So, these are the methodologies we're using: system dynamics process, ordinary differential equations, stochastic models. Some of the tools we're using are Stella, Vensim, DE-Solve. Model calibration. So again, data science approaches like the Powell optimizer, Hamiltonian Monte Carlo for fitting of data, and also measures to assess the fitness of the models. And then we use a lot of data analytics through the R language, things like dplyr, per, ggplot2, etc. So behind it all, it's a model building process, but I think data science plays a very important part because we're using lots of tools, things like calibration and also visualization, etc., using a number of different tools. So that's really an oversight of the model building process itself. So on now to our Pandem II project, which has started in February of 2021. It's led by NUIG, the School of Medicine with the School of Computer Science and the Data Science Institute. It's led by Professor Maura Connolly of the School of Medicine, and we're looking at developing informatics solutions for efficient EU-wide pandemic preparedness and response. The goal really is to work with EU countries to better prepare for future pandemics And this modeling work I'm presenting today is a very important part of the project, because you know, when people want to see how they can prepare for pandemics, they want to have be able to run models to see things like, you know, have we got sufficient resources, what's the impact of disease spread, etc. So it's a very important project, and we've got some excellent partners, including public health agencies from Germany, Sweden, the Netherlands, Portugal, and Finland and Romania, and also first responders. And the project then involves a number of different work packages. So we've work packages on surveillance, situational awareness, pandemic planning, and the work I've done today really, I suppose, fits into this part of the project, where you're looking at tools for pandemic planning and how you can you know, use models like the SIR model and extensions of that to help with pandemic planning. Communications is a huge part of pandemic planning as well, and that's an important work package. And we also have network and demonstrators, which will be at the end of the project. So in many ways, this is the goal of the project. Again, it's great to be involved with so many partners working on such an important challenge. And again, the goal here is, if we go back to an earlier diagram, you know, if you look at health protection, a virus comes along and everyone's at risk, and then you can reduce the risk over time. So I guess this is time as well, going here on the horizontal axis. So people are at risk, people are at reduced risk, maybe from things like you know, reduced of contacts, etc. But then people are very low risk eventually, where we get good vaccination in and people then are protected. So the goal of the project really is to support this process. So we're going from, you know, a novel pathogen comes along, suddenly everyone's susceptible, so therefore you need systems in place like surveillance, you know, where is the pathogen coming from? Can we detect, for example, outbreaks, etc., and, you know, the disease spreading from country to country. Situational awareness then gives people an idea of, you know, what's the current situation, things like, you know, dashboards with the behavior over time on the dashboard, etc. Pandemic planning says, well, you know, if this happens, how well prepared are we? And so over time, then, are we vulnerable? Do we lack resources, etc.? So this is part of the pandemic planning. Communications then is how best do we communicate with the public, etc. And so can we get a good message out there and show people the importance of things like you know, countermeasures like social distancing, etc. And then also the demonstrator then will be to show it all integrated together and present that at the end of the project. So that's the conclusion of the talk, really. I mean, the idea really is to give an insight into how we can combine two different methods, system dynamics and data science, and see how they can be applied to a very important problem area. Again, a quick look at the SIR model and how this can be a foundational model that provides insights in terms of how to mitigate a new pathogen that's and indeed a new pandemic. Also, that modeling is iterative. Again, it's very important to work with the experts, work with public health experts to get good data and to have a very good process for building models. And also NUIG then is working away on applying these methods as part of Pandem II. So that's just the conclusion. Just a special thanks then to the organizers. Thanks very much. It's great to get a chance to present today. I really appreciate that. Also, give thanks to my colleagues in the Irish Epidemiological Modelling Advisory Group, IMAG, the Department of Health and the Pandem II project. So again, this group is chaired by Professor Philip Nolan, who's done a fantastic job of getting over 33 modelers working together for the past 15 months. And it's been great to be part of that as well. Also thanks to my colleagues in NUI Galway, School of Computer Science, Ryan Institute, Insight Centre for Data Analytics and the Data Science Institute. And also a special thanks to my family over the last year, who've been fantastic in their support during the time I've been working on this project. So that's really that's the presentation.